All right, we're going to be talking about what do we do if we have a distributed charge on a solid disk. All right, so here's our solid disk. Questionable. Our goal is to figure out what is the strength of the electric field at location P. I don't know why I wrote a T. At location P. So here's location P. This is a solid disk. And luckily, this is going to be right down the center. So we are going to have symmetry. So life is going to be good. Some other fun facts that we should be aware of is, let's make this a little smaller, that we have that's better, charge density on the disk of so. And remember, charge density is defined as the charge per unit area. And since the ratio, that would also be dq dA. All right, so we want to keep that in the back of our head. Always kind of remember that stuff. So again, just to go through the basics, if I look at this, I have to find the little piece, because if we've got, say, a ring, radius r, length x away, all right, and if we said, well, okay, this is a piece of charge, but the charge is everywhere, so how do we do this? Well, if we think of a disk as a series of concentric circles or rings, like, say, a tree, so if you think of a tree, if you cut the tree in half, you have a disk. All right, you're looking at a disk, but that disk is composed of not an infinite, but a finite number of specific growth rings. So a disk is actually the sum of all the different individual rings. So each of these rings is our little piece of charge, but it's also our piece of our area as well. And so if I were to say, look at a point here, it's going to, why stop shifting on me? It's going to create a piece of the overall electric field. And then the same thing down here, just like we've done before with the ring. We have another piece of our field, but the y plane is going to cancel out. And so the only part that's actually going to create this electric field is the x plane. All right, so DEX. So we are going to remember our equation from last video. So this would be the electric field from a ring. That was equal to K x q over x squared plus a squared, where a is, this was that was at radius a, to the 3/2. All right, so that was in our last video. So if you don't know what I'm talking about, I highly recommend watching that one first, or else this is going to be a little confusing. So we are going to look through all of this fun stuff, and let's hack and slash to figure out what it is for a solid disk. So we're going to start here with this, but we are going to say, well, this would be the piece of the whole. So dE is equal to K x dq, that'd be the piece of charge, times x squared plus, and then here I'm going to use that r. All right, so we have r squared to the 3/2. So now we have to say, well, okay, what does all this stuff mean? So that's where we go back to this information here. Let's make that smaller. And we'd say, well, some stuff we know is that area, right? We're looking for a disk, so that's going to be pi r squared, but we don't want area, we want dA. So that means dA would be the derivative of that. So we got 2 pi r dr. And again, 2 pi r, that would be the circumference of a ring. dr, you're going to integrate over all of them as we go around. And in terms of what does this actually mean, remember this right here, this would be my length, how far around, and this would be my width, because area is length times width, because each one is infinitely small, so that's the dr. Now we also have in our back pocket this information from on the right over here, all this stuff. So we're going to rearrange this so that we have dq is equal to theta sigma. I forget what that one is. That's sigma. dA. Doesn't matter what you call them. And then we can say, well, I know dA is this. All right. So I'm going to end up with dq is equal to this guy times 2 pi r dr. Cool. Now we've gotten some variables that make sense. The reason why we want these variables is because at the end of the day, this right here, this r, this is going to be a constant. Or I'm sorry, a, right? A from the previous one was a constant. R is our variable, right? Because we're going to be going different radiuses. And this overall charge is going to become our pieces of charge. So now we're going to smush all this fun stuff together. And we have dE is equal to k x that guy 2 pi r dr over the quantity x squared plus r squared to the beautiful 3/2. Really ugly stuff. But if we integrate this, we're going to get our e. So now we have to integrate this bad boy. Doot. That's going to get our overall stuff. Now, integrating this is a nightmare. And the beauty of this type of thing is that you can just look up in table. All right, there's table in the back of your book. I believe it's like B.5 or A19 or something like that. I forget. But on the exam, you will get situations where you look at it and you're like, I don't know how to integrate that. There is a series of integrations on the AP cheat sheet as well. So once you look this up, you basically see there's a format of, well, let's pull out all the constants first. So let's go that route first. So if we pull out all the constants, okay, x is a constant because it's a known distance away. Constant, integrating from r to 0 of r dr over this garbage. And this is in a table. All right, so this is what you'll actually find in a table, this chunk here. And so if you look up that in a table, you'll basically see that there's something in the table that just says x dx over x squared plus a squared to 3/2 equals this fun stuff. Negative 1 over x squared plus a squared to the 1/2. Why? Don't look at me. I don't like calculus that much to figure that out. But you can just look it up, and that's going to make our life way simpler. So now I can say, all right, well, with that knowledge, I'll scroll up here a bit, because now we're just doing calculus. We get all this fun stuff. I will also be replacing k, because remember, k is equal to, I gotta reduce the thickness on these. There we go. K is equal to 1 over 4 pi epsilon naught, just because you might see that. So then I'd be like, okay, so this is also 2 pi over 4 pi epsilon naught. That dies, that dies, that dies, that becomes a 2. So really what I have here, if I then combine this back in and bring it down with this, I get my new setup of x over 2 epsilon naught. And then I'm integrating -1 over x squared r squared to the 1/2 between r and 0. And so when I do that, you get to go down the list, and you get this guy. Because right now I'm just doing a whole bunch of calculus. So x squared r squared, make that capital Cis, to the 1/2. Let's see, minus a minus. Yay, love those double negatives. X squared to the 1/2. Hey, at least that cleans up nicely down there. So at the end of the day, my electric field at point E for a solid disk be equal to x times the charge density over 2 epsilon naught, because I did the whole k is equal to 1 over 4 pi epsilon naught times 1 over x minus 1 over x squared plus r squared to the 1/2. Ta-da! So what's the big takeaway? All right, so let's go back and let's examine the things I would actually care about. So 1, here again we have our image. Make it thinner. All right, so that's our setup. Here we have our charge density. All right. And then here we're able to actually use something from before. So that's our piece of the electric field that we're able to use since it's a bunch of rings. And then here, all this stuff, we are gathering all the pieces. To have one variable, and that variable we wanted was x, because it was the charge a given distance x away. So we wanted to get all the pieces. And then after that, this is just all calculus. And remember that if you're taking the AP test and it gets to the point you're like, this is calculus, feel free to walk away, and you'll basically miss 1 point. And so you could ask yourself, Miss Mansky, is all this stuff here worth 1 point? The answer might be, yeah, it's really not worth all that for just 1 point if you got the majority of the points elsewhere. So keep that in mind. Kind of looked busy by the end. Hopefully this was helpful in evaluating the distributed charge for a solid disk or pretty much any 2D object, because if it was a rectangle, then you'd say, well, it's a line. It's the thickness of the line times d, your width. So you'd have like your thickness of your line, and it's dx. And then you'd be like, well, then this distance is x, blah, blah. It's all little pieces, those lines put together. Makes your piece of paper your rectangle there. So shapes can be combinations or integrations of the smaller pieces. All right, that's it. I'm done. Peace.